Hey everybody. So this is going to be the last of the videos for this first Grasshopper assignment that I'm going to cover. And this is the optional additional piece to make things a little bit more interesting. So I was originally just going to do this sort of simple paneling script, but I've decided that, one, it was kind of simple and we can do something a bit more interesting with it. So the output of this thing is actually going to be not only sort of paneling like this, but it's also somewhat adaptive paneling where the size of the opening here is variable, but also we're going to make this so that it is printable with just 2D printing or laser cutting. And what that means is that we'll take this and we'll export each one of these individual little faces so that they could just be sent to a laser cutter and you could cut this whole thing out and assemble it. So you can actually take this thing that you make in Grasshopper and make it into a real-life object. Of course, you could do the same thing with a standard printer. You would just have to do the cutting yourself. A laser cutter, of course, would be preferable if you have access to one. So this could be an interesting technique for model making, for example. If you were interested in trying to make a sort of complex surface like the one you see here, you could make it out of a series of faceted pieces, and that's what I'm going to cover here. So this has actually evolved somewhat since the first time I started writing this. I realized I could sort of be a bit more efficient about some things, so I've rewritten part of it as the sort of iterative process of working with Grasshopper. Oftentimes when you write something, you write sort of a long, complicated version, and then as you sort of look at it and play with it, you realize there are sort of smarter, more efficient ways of doing things, and you come back and you sort of improve upon your work. So that's why, like, when you initially write things, you do it a whole bunch of different times, a whole bunch of different ways. And sometimes it works, sometimes it doesn't. And sometimes you just realize that you could have made the whole thing simpler. So the basics of this is that we're going to take a surface. So we need to create a surface. So I have, and this is going to be one of our outputs, but I'm going to get rid of that. I have two surfaces here. I currently am in the wireframe mode because it's a little bit easier to see once you start applying a pattern to a surface. But just so we can see what it looks like, we have two surfaces, as you can see here. I still have my backside of the surface set to be a separate color just so I can see what my normals are. It's actually not going to matter much for this, but it is, I think, always a good idea to be aware of where normals are. And again, probably won't matter for this. But I have two surfaces here, and I wanted to bring up one distinction that will make a big difference when you start to do paneling like this in Grasshopper, which is if I click on this surface here, which I just kind of created by drawing out a sort of simple four-sided surface, turning on points on, and just pulling these up. So since I pulled up the two opposite sides, I have made a complex curvilinear surface. So every single piece of this surface is curved in two directions, which makes it incredibly complex to physically model, as nothing is planar. Now modeling in Rhino, of course, is fairly easy. And then I also have here what is a torus, which is the sort of round primitive that you can use, this guy here, that I cut and quartered and basically made into sort of a half donut that's cut. And it's one thing I want to show you guys, which I think is really interesting. So when we have our sort of output here, which I'm going to skip down to the end, if I were to apply this same thing to my torus, it's probably going to break, and it broke right away. But one thing I wanted to show, in part why it's breaking, so you can see here actually when it loads into Grasshopper, it's going to load in just this portion of the surface. But as soon as I start doing operations to it, it's actually going to consider the full surface and not just the trimmed portion. So again, if we look at this thing, it says trimmed surface is its object type as opposed to just surface. And a trimmed surface just it's aware of its original identity that it used to be a larger surface and it no longer is. However, once you start doing operations to it, especially ones that involve UV values, well, it wants to use its original UV values in its original surface form. So a lot of operations in Grasshopper will simply either break or do unexpected things like have you making operations to the whole donut here and not just the portion that you were looking at. All right, so anyways, I'm going to use this sort of single regular surface here. And of course, I'm going to recreate this guy. I am going to follow it as I do it because this one's a little bit more complicated than some of the other ones I've done in the past. Nothing too complicated here to follow along with. And actually, this is probably one of the first ones that we really don't have to manage grafted data at all, which grafted data is, in my opinion, the most complicated thing in Revit or Grasshopper. So anyways, first thing, as usual, I need to create a surface param that I can load that surface into Grasshopper with. So just type in srf, get one of these little boxes, set surface. So we need to divide up this surface. And in the past, we did a divide surface, which sounds exactly what you would want, but it's not. We actually want something called isotrim, which, to make things a little bit more confusing, the label here says subsurface or subdivide surface. But if you search for that, I guess isotrim does come up. So that's a good thing. We also need to supply this a domain. Now it's specifically looking for a particular type of domain, which is a domain based on that surface that we just input. So we need to do a deconstruct, a construct domain. And there's a couple options here, but we want to do, actually, which one do we want to do? Divide domain, I'm sorry. We want to do divide domain, and it's the one that is squared. So it looks like that. It's the one square becoming multiple squares, divide domain squared. So we're going to input the surface into the I value. We're going to need a U and V, so I'm just going to hit 11, copy that slider twice, just so I can get that slider that goes between 0 and 100. And I'm actually just going to set both of these to the value 4. Again, whenever I am first developing a definition like this, I always like to keep the numbers small initially and raise them later once I have a sort of working definition and am less worried about it sort of crashing and breaking because of too much data. So we can see here, again, I'm going to go to wireframe mode so we don't see that surface anymore. We only see the Grasshopper output. Now I'm actually going to hide the ISO curve too, so all we see is that nice Grasshopper surface now. So we can see here, it's still quite smooth. All of these surfaces are, it was broken up into 16 individual surfaces. So if we look at the output here, hover over, we can see there's 16 untrimmed surfaces. And that's each one of these little squares that you see. These are by no means planar, as the original object that you cut it out of aren't planar. And our first task is actually going to be making it planar. So we're going to use something called fragment patch, which essentially will attempt to triangulate things. So if we put that in, we can now see we have a nice faceted surface. So the great thing here is basically it subdivides those little squares into triangles. Triangles, having only 3 sides, are always going to be planar objects. And planar objects are essentially a necessity for a lot of real-life construction, as they are materials that can come out of any sort of flat material. So anything that you can laser cut, CNC mill, hand cut, you can make is a planar surface, and you could facet and fold together into something more complex. So we need this to be made out of planar surfaces, and the easiest way to accomplish that is to use triangles. There are ways of accomplishing the same thing with squares, but it is much more complicated because squares are not inherently planar. But these triangles are. I mean, this shape here was originally a rectangle, and you can see how unplanar it is. And again, planar just means flat, perfectly flat. So it's actually kind of interesting looking already, so that could be a cool little project in and of itself, but that's not where we're going to stop. So first thing we're going to do is we're going to do a deconstruct brep. So what that's going to give us is series of faces, edges, and vertices. So vertices are the connection point, edges, of course, are the lines, and faces are the individual faces themselves. So we're going to get an area now. And actually, we might not even need that command, now that I think about it. Sometimes you can actually optimize these things as you're running through them. We'll see if that ends up working out for me or if I end up needing that after all. So why I did an area is I actually want to be able to drive the size of those offsets that I'm eventually going to make, those things, the sort of openings in the panels, based on some kind of input data. So we're going to use an attractor system like we used in the 2D paneling, panel that we did as the second portion of the assignment. So in order to do that, we need to have a point that we can reference in each one of these, and an area command will give us the center or the centroid of each of those little areas. So we can do a distance, and I have a point that I've already sort of placed in here, just a point in 3D space. So I'm going to load that in as well. Right click, of course, to set that point and make a nice little distance between these two. Oops. Set this again. So now I could do just what I just did there. However, because the areas, as you can see here, these points are actually in three-dimensional space, while I drew that point on the sort of XY axes, the distances are not only going to be affected by sort of in plan where that thing ends up being, so it's also going to be affected by the height. And I'd rather it not. So what I'm actually going to do is remove the z height data from all of those points. So I'm going to do a deconstruct point, take these centroids. So that will give me individually the x, the y, and the z height. And I'm just going to do a construct point. And in this case, I'm actually just going to plug in the x and a y, because the z is going to default to 0. So it will just give me points, as we can see here, that have no z axis to them. So now, if we plug this in, the distances are only going to be on the xy axis and not on the z axis, which again, I just prefer in this case. You could do it either way, but in this case, I'm looking for that because I only want to be making that comparison because I'm not really moving this point around in three-dimensional space, right now at least. Okay, so once we've done that, unlike what I've done in the past, I want to be really specific about the sizing of these offsets. I want to be able to set the minimum size, and I want to be able to set the maximum size. So I'm actually going to do a graph mapper now, which is not the way I've done it in the past in the other videos. And the reason being is I want to sort of be in control of how exaggerated my data is. And again, I'm just going to use a power here before I remap it, so that when I remap it, I can remap it to be specific values. And again, I will just show you what that does. So I'm going to do a bounds. And do a construct domain, 2 values. I'm going to set each one to 5 right now because I want a slider from 1 to 10. And a remap. So standard thing, I do the same sort of operation all the time, as I'm almost always remapping data or doing it very frequently. It's probably my most used sort of standard set of modules to put together. Because you're always messing with data, so it's just a useful thing to be able to sort of really be in control of what that data is doing. So basically, what this is going to do is I'm going to set this to be a value of 1, and we'll do a value of 6. So now when I take the output here, which I just got a multiplication, but I'm going to do a panel real quick. So what this is going to mean is that despite having my curve here, no matter what I do, my values are going to be between 1 and 6 because that's the remapping is happening after that curve. So even if I go crazy and make a huge exponent, it's still going to be between 1 and 6. And why that's valuable is I can then, when multiplying, ensure that my offsets are at a minimum, whatever I set here, and then multiplied by that. So they, in this case, the offset will be as small as 2 and up to 12. So multiply 2 by 6 in that case. So that's a fairly simple thing. Now we're actually going to go back and we're going to do an offset surf. So we did all of this just so we can do this one command here, which is going to take looks at it wants some curves, but in this case I'm actually just going to feed it to surface, and it wants a distance, and that's what we got here. I'm going to feed that in, and then it wants a surface to operate on, which we're going to feed the surface again. So now if we look in the Rhino, we can see that we are offsetting interesting. So it's not doing what I was expecting. So it's offsetting the full square surface and not what I intended. So that was actually the reason why I had to do the deconstruct B-rep. So it seems for whatever reason, it doesn't really want to keep this fragmented quality. So I will need what I had done, which is the deconstruct B-rep, which ensures that I'm only working with a series of faces. So I'm actually, since I'm going to plug a bunch of things in, going to turn off my solver real quick, so I just avoid the issues of a bunch of new data trying to be processed at once and it crashing. And I can already tell that I'm glad I did this, because as I plug these in, I can see it's grafted data simply by the fact that it is a dashed line. And I know I don't want grafted data right now because I don't need to manage the individual lists. I just want this to be flattened. There's no advantage for me to keep that separate for any reason. So that would only be useful if I was trying to match up the faces with the edges, because the edges would be, so if we just look at this panel real quick, you'll see why. So it's not going to show anything because our solver is off. So we're turning the solver back on. So right now, because this is flattened, we can just see we have a series of surfaces. But what it would have been is it would have been all the edges associated with each one of these sets of faces. And then all the vectors associated, vertices, I'm sorry, associated with each one of those. But we don't need to keep those organized. We just want those faces. So that's why I'm flattening. And again, so the first thing that happens is we get the area, we deconstruct that area, or the centroid there, so that we only have XY values. Then we can make a comparison to the point that we have placed. We use a graph mapper to control how that data is manipulated. And then we remap it to be between a certain set of values. Now we may adjust this later on as we start playing with it. And then we have a multiplier for those values. So a bunch of complex things to get to this point. Now I'm going to play around with this a bit and get it a little bit more refined before I start doing the next steps, because the next steps tend to slow down a bit, although the offset is actually the slowest portion of this. So let's say I wanted to go to a sort of denser screen. So let's put in 6, and it's going to be a little slow with each one of these, because every time we add UV values, we are making the offset at the end slower. So you can see now we've panelized this a bit more. So I think I'm happy with that. But I want to really have a high contrast between the offset that's happening in my smallest panel and the offset that's happening in my biggest offset. So I'm going to try increasing this value first to 3 or 4. And now we can see that there's a pretty good difference there. So if we upped the, let's try adjusting the graph mapper here. So we can kind of see right now, but basically the relationship of how this is adjusting the fall off basically. So how quickly does it go from its sort of biggest to its smallest? And then this is the ratio between the biggest and smallest at this point. So the smallest or the biggest offset is 6 times the smallest. So now it's 7. Now, if we go too far, they will break. Basically, it will no longer be able to create a surface because the offset was too great. You can see here, that's about the limit. But every one of these is going to have a unique offset. And if we drag this guy around, so of course this is a bit of a slower operation now. So won't be instantaneous, but we can get an idea of how this affects it. So it's looking pretty good. I'm happy with that. So maybe in this case, the logic is as it stretches up, it wants to get thinner because maybe it has more sort of stretching out in the direction of the vertical direction. So I'll place it there, approximately center of that panel. As it comes to the ground or in the lower portion, it's a bit denser. Of course, we could do multiple point attractor, similar to how we did in previous ones, but I think for right now, the single point attractor will work fine. So I'm going to say I'm happy with that. So we're going to move on to the next step, which I'm going to add a fillet and a radius to that fillet. And I just put a slider in, take the curve, add that to the fillet. And essentially what that's going to do is round those corners. So we can see what that looks like. I'm going to go for something nice and exaggerated, like 10, which might actually even be so much that it's eliminating some of my panels. No. 8 looks fine to me. So nice rounded corners. Again, that's more of a stylistic preference, but I think it makes this look nice and space-agey and interesting. And again, I don't want to have anything grafted, so I'm going to flatten as I go. So anytime I see those dashed lines, you know, if you're combining grafted data with other things, it's an easy way to really screw up your operation. So the next thing I'm going to do is weave. So in the past, you'd see me drag multiple things in to one spot by holding the shift key. Weave essentially allows you to do that, but do it more intentionally. So I want to actually take these original surfaces and weave them in. And basically what that's going to do is at this point is going to do some grafting. And I'll show a panel to give you an idea. So essentially, we have a bunch of closed planar curves. And we have a bunch of, where'd it go? Trimmed surfaces. So what this is going to do is weave is going to put a closed planar surface and a trimmed surface with each other, or at least woven right next to each other. So then we can do a boundary surface so that we can combine these two. And now you can see basically the first surface is cut by our little curve that we have there. And then I'm going to do one last thing. Well, I'm going to do a couple more things. So these are still flat surfaces, meaning they have no depth to them. So, you know, if we were building this, realistically, I would want to do an extrusion to these, which I'm going to show. However, before we get there, I'm going to sort of show the process that you would want to go through if you were actually trying to make this into something that you could laser cut or print and cut out. So what we're going to do is actually, after we've joined these, I'm going to go bake. And since they're joined, it doesn't actually matter. Create this guy, which is a open poly surface. So we can see here, it's a nice little pattern. We're going to perform a command in Rhino now, which is the unroll SRF, unroll surface. It's going to ask us, do we want to explode? Sure. Do we want to keep labels? Sure. And keep properties? No. I'll just leave it at this. And essentially what it's done is it takes all the individual faces and places them flat in your Rhino file. And essentially it gives a number. These are just little tags that are on this that shows how they connect. So if you look back here, it gives you the key. 90 is next to 93, or I guess this surface here would have a 91 and that surface would have a 91. So you can just kind of use that to assemble this. So you can know that if you have a 41 here, you need to find the other 41 and then those will go together. And because they are all unique shapes, they only fit in one place. And if you put them together, it would inherently just start forming this shape. So this is how you can take something from Grasshopper, something this complex, and actually make it feasible to really construct this thing in a fairly efficient way. So you can see here, this says number 44, this says number 44. So when you print this off, you would just put these two ends together. But it's a cool little command to make faceted surfaces into something you can build in reality. And you can see here, it's up to 176, so your labor certainly goes up. The more facets you have, there's more things you would actually have to put together. So that would be one thing you could do. Pretty cool little thing. Of course, the other would be to, we'd want to give this some three-dimensionality if it's going to really be a part of a project that we're going to use. So we want to do an extrude surface. And we want, in this case, to get a particular direction, which is going to be normal to the surface. So we need to do a evaluate surface. And Okay, so sorry. So we need to basically give a UV value. So I'm just going to do the same command I did earlier of area, which is going to give me the centroid of each surface and plug that into the UV. And then use the normal here as a direction. We'll have to give it an amplitude. So a normal in this case is a vector that doesn't have a force applied to it. So if we do amplitude, we can take the normal, plug it into the vector, plug the vector into the distance, and then put in, say, a value. Now 5 is going to be way too much, probably. But go back to, so realistically, you know, this might be, say something you would be cutting out of a, you know, this might be a metal panel of some sort, in which case maybe it would be not 5, whatever inches thick, but maybe something more like a 1/4 inch. So I'm just going to set this to 2. I did not build this at any particular scale, so I don't really know. That looks about right to me. You can see they have thickness now. So if I were bringing this into a model, I'd want to make sure I extrude it first. And then I could bake this and group. And now let's just go to, how about an Arctic view? Of course, we have the surface there still, so I'm going to hide that. But then we get to see what this thing looks like. I'd say pretty nice. So again, you may want to, you know, if you were really thinking about what you would drive the sort of openings here, there's a lot of things you could do. You know, I mentioned probably previously that there's a Ladybug as another plugin for Grasshopper that you can get that allows you to use solar data. So you could theoretically use solar data to drive this, where it would actually be based on, you know, calculable solar heat gain that you would get depending on how this is configured and where it is on your site and what it's covering, and use that to actually determine the size of these openings so you'd be your most efficient building size. Anyways, that's going to do it for this demo. So basically, this is how you create it to be a 3-dimensional object. And if you wanted to actually print it, you'd want to do the, well, skip this step, basically everything after boundary, join the things and bake that, and then take that and do an unroll surf to get these little things on the ground here, which you could then print off somehow. Okay, that's going to be it. Thanks.